Good morning, students. Can you hear me?
Yes, doctor. Good
Yes,
morning.
doctor.
Good morning. Today is Monday, October 11th, and we're going to continue with our study of finite elements applied to the case of bars. Okay, one word of warning. Starting this past Friday, for some reason, some sessions, I don't know, there was some change, I don't know what, in my account are restricted to 40 minutes. Okay, so if the session stops, be patient, okay? I will restart the session and Engineer Isaac will allow you to come back to the meeting, okay? So please be ready for that. Okay, we're going to continue with our study of deducing the stiffness matrix of a bar element, okay? We have started to review basic equations of bars. So that's long elements supported only in plane in longitudinal forces or loads. Okay, so we're going to continue with that. And then we're going to prepare an example. So you see the full application. Here, these are the assumptions. Displacement small, linear elastic range. The section of each bar element is going to be considered as constant. And of course, this is not really an assumption, it's just a specification. Since we're working with bar, that means that the loads that will be applying on these elements are longitudinal, okay? If we had this type of load, lateral, that would be a beam. We're going to deal with that in the next chapter. Right now, long elements with longitudinal loads, that's the case in this chapter, okay? So here we have this case, and you see that we have distributed load in general. That's force per unit length, okay? And we're going to call that force per unit length as little f. We could have concentrated forces. And in that case, remember, we can represent these concentrated forces as delta Dirac functions. So there is no problem for that, okay? So we take an arbitrary differential element down here. Since this is part of this bar, which is indeed in equilibrium, every arbitrary element has to be in equilibrium, okay? So we make this cut on the left edge, and here we have this force. This is the internal force in the x direction, similar to the shear force, similar to the bending moment. Internal, those forces appear when we make a cut. That's what we call the section method, okay? Now, if we make a different cut at this position, okay? This is a positive phase. So the positive force points to the right, but the value has changed a little bit from the value that it had on the left face. So this little change is what we call dp, is the differential. Okay, now if we go from here to there, the only change that we have had is in the x direction. So this differential will depend only on the x. Okay. Since we assume that the section is uniform, okay, we could specify this force easily as a product of the uniform stress times the area, and the area is constant, okay? So this change will be related to the force per unit length, which is applied in this piece of element. Okay, so we have this force, which is different, and then this distributed force on the element. And these three, they have to cancel and keep this differential element in equilibrium. Okay, so let's continue with our deduction. So today is okay. So we say summation of forces in the x direction has to be equal to 0. That's because we are working with static equilibrium. I think the thickness is too high there. Okay, now what forces we have? Okay, let's consider as a reference to the right positive. Of course, we have this and that. So we have P plus dP pointing to the right plus, this is force per unit length times dx, that's length. And then we have this P of x pointing to the left. So we subtract P, okay, and then has to be equal to 0. We cancel this with that, and then we recall what we said previously, that the only force that that the only change that we suffer in going from this side to this side is in the x direction. So this differential here has to be expressed as the rate of change in the x direction times dx. Okay, so we can cancel the dx. And we can say that the rate of change of the axial internal force has to be equal to minus f of x. And f of x is the force per unit length in the x direction, of course, applied on a differential element. So this is equilibrium. Now, what else? We can express this large P, okay, this, we can say since we are working in the elastic zone of the material, and because section of the bar is uniform. Okay, in this case, we can say that the force P, okay, the force P is simply equal to sigma x times area. Okay, if we had a change in area, okay, a good change in area, probably this sigma x is not going to be uniform. Okay, right now, we're considering that if we have a section like this, okay, the stress is going to be uniform. This is typical because in general, when you have constant section, okay, you don't expect to have much of a variation in the y or z direction, okay? So that's that. And since we said that we are in the elastic range, we can say that this is equal to E times epsilon x and times the area. And finally, we can say, remember that we define it, the strain as du dx. There. So the axial force can be expressed like this. Okay, so remember this relation this is a differential equation, can be applied when we have to set equilibrium. So if you had an statically determinate case, this is going to be enough. Okay, if you have an statically indeterminate case, then you need something else. And that something else is this relation, because in this case, we are using extra information. And that extra information is the Hooke's law and the assumption that the section is uniform, and we can assume that the stress is uniform on the section. Okay? So if we replace this into here, we can deduce a second-order differential equation, which can be applied when we want to analyze bar problems, determinate and indeterminate cases, okay? So we can say that replacing this in the equilibrium differential equation. Okay, so we put this into here instead of P. So we're going to have the derivative of respect to X, but E is constant, A is constant, so you are going to have the second derivative of that. So this is what we have there as a result. So we said this is EA, the second derivative of U with respect to X, and this is going to be equal to minus f of X. Okay, so this is the equation that we can use in order to solve these problems. Okay, this is the second order. That means that boundary conditions are values of, in this case, the function that we try to determine is U. So it's going to be values of U or the first derivative. Okay. In some cases, you have values of P. Okay. So, as we can say here, if we know the value of P, okay, you can take the E and A down here, and that will be the value of the derivative. Now, I'm going to write that just in case. I'm going to put it like this. Remember that if you know on a boundary the value of P, the condition may be set as, okay, so you know the value in one end, right? So you know that Pi, for example, on this end is equal to EA du dx at the end. So we can set that the derivative at the end has to be equal to P divided by EA. So if you know the value of P, okay, you know EA, those are data, classical data, you can specify the derivative in this point as a boundary condition. The other classical case is to know the value of the displacement, U. Okay, now, so that's, if we need to solve analytically a problem, that's the equation that we can apply, or to solve, not only apply, but solve. Okay, now let's go to finite element. Now, let's go to finite. Please, these relations that we have reviewed, because this is just a review. You studied all of this in solid mechanics. This is just a review. We're going to need these equations in order to analyze results, in order to establish, you'll see equilibrium using the stiffness matrix. Okay, so let's do this. Okay. Now, let's consider, for example, that we are going to analyze one structure like this one. For example, let's suppose that we have this structure which has two legs. Okay, we have something like this, and like this, something like this. See, you want to analyze this. And these are pins. That's what I'm there. Okay. So since these are pins and the weight, let's assume that the weight is neglectable. Okay. What we can do is we can take each one of these and analyze. First, we're going to analyze it independently. And then you will be patient, we'll analyze as a combination. Okay, so let's start by saying, okay, we're going to take, no, what happened? But, okay, let's consider this element, and we're going to take it independently. So let's analyze the equilibrium of a single bar element. Okay, be patient, I insist. Next subchapter, we will put the whole thing together. But right now, let me analyze one single bar element. Okay, let me save just in case. Okay, so instead of analyzing in this position, see, it's better if we put it. If we put it horizontally, okay? Okay, so this is the element, okay, that we're going to analyze is this one here. And in this case, we're going to define, okay, since we're analyzing one single element, we're going to define this coordinate system. It's what we call a local coordinate system. Okay, that's why we use this hat, because this is local. In the same sense, in the vertical direction, this is what we call the local reference system. Okay, so you can imagine that each one of these elements will have a different local reference system. It is true. So we have to set up something in order that we can set the equilibrium of the whole structure, but be patient. What else? We need to define the joints. So we're going to have one joint here and another joint here. Okay, so remember the first step in the finite element is that we have to discretize. And this is what we're doing. We're saying that we're going to take this element, okay, and we're going to consider that as one piece. This is the element that we're going to analyze. So this element, of course, is going to be defined by this joint, joint 1 and joint 2. What else? On this element, I am not going to be interested what happens in between these joints. This is a discretization. We are going to be interested only what happens in the joints. Okay? So if we have something here, we're going to be patient, is to transform that into equivalent loads to be applied in the joints here and here. Let me change color just in case. Okay, so we have, so we have to the right is one force, F1x, and we're working in the local reference system. And here, we also have one F2x vertical. So we say this is the local reference system. So that's going to be one local reference system for every element. Okay? And we say that Fix local, this is external force applied in the ith joint. This is just a specification just in case. Okay? Now, what was the next step? Remember, we mentioned that there are two phases in the finite element discretization. The first one is to partition. That's what we have done. We have taken one single element. And the other step, the other phase was to establish an interpolation. Okay? So, to continue, we are going to set an interpolation function for U in the element to approximate the solution. So remember, we're working only in one single element. Okay, so let's propose something. So what we can do is we propose the simplest way. This is an approximation. This is not exact. And we're going to be expressing that approximation in the local coordinate system. Now, since we have only two joints, okay, we can set this function to recover the value of the function on the left and on the right joints. So we have only two conditions. So what we have to do is we can include two constants to be determined in a minute in this expression. So the easiest way is to say that this is equal to A1, okay, plus A2 X local. And this is going to be valid only in this element. Okay, now let's find A1 and A2, and to find the constant A1 and A2, what we do is we evaluate that on the left and on the right. So let's suppose that we have this U. I just received a message saying that the session will stop in 10 minutes, okay? I warned you at the beginning. So we have here U, and this is local X, and this is the length of the element. So on the left joint, let's suppose that we have a value, let's call it D1X local. And on the right, we have a value, we can call it D2X local. Okay, now what we have done with this function is to assume that the distribution will be something like this. Damn it. Sorry, I am having problems with this thing. Sorry. Damn it. Ah, shoot. Okay, so we go from here to there. This is a straight line, believe it or not. But this is just an approximation. Okay? So what do we do now? We evaluate, Jesus. We evaluate, damn it. This function, so we say we evaluate U at 0. So if we evaluate it here, we have to recuperate D1. So we say that this is equal to X is 0, so we get A1, and it has to be equal to D1X. And in the other end, you see that you evaluate it here, you have to recuperate D2X. So this is going to be equal to, we evaluate this at L. So it's going to be A1 plus A2 times length. Damn it. Okay, so immediately we see that A1 is equal to D1X. So let's find A2. So A2 is equal to A1 minus. Okay, but A1 minus is equal to minus D1X. Okay? And that's to the left, but on the left, let me erase. Okay, A2, that's the constant I'm trying to find, is equal to U or L. U or L is equal to D2X. So it's going to be D2X. And then I take this A1 to the left. So it's going to be minus A1 is equal to D1X. and we divide it by L. There. So we have A1 equal to D1x and D2, and A2 equal to this ratio. Now we can replace back into here, and we can say that A1 is equal to D1x, and A2 is equal to D2x minus D1x divided by L. So immediately we can say that U of x is equal to D1x, that's A1, plus this D2x minus D1x divided by L, that's A2, and times x. Now, what we do is, this is an approximation. What we do is, we express this as a product of one row times one column. And here, I'm going to put D1x and D2x. Remember, these two are the unknowns right now. So what is multiplied by D1 here? I found it here, so it is 1. And I have it here also, so I have it minus x divided by L. So I multiply this times that, I have this and that. And D2 is multiplied by x over L, so I have x over L. Okay, so right now, assuming that this linear distribution approximates adequately the solution U, okay, we can express this function U as a product of this row. You see that it's completely known times D1, D2. These are the unknowns, okay? So this is something that we mentioned in the previous session. This is known. This is unknown. We do not know these two values. And this is polynomials known. See, 1 minus x over L, x over L. So it's completely known. It's in some cases, it's useful to draw these polynomials. Okay? We can call them, for example, Ni. So if we draw this, it starts in 1 and linearly decreases to 0. So this is N1. And N2 starts in 0 and linearly increases up to 1. There. Okay, that's something that you probably remember using Lagrange's equation, Lagrange's polynomials in numerical analysis, right? Don't say no, yeah, that's something that you studied there. Now, let's go on. After we have U, okay, we can calculate, let's calculate internal axial force. So we say that P is equal to EA du dx. Now, this is an approximation, and in the local reference system, we're considering only one single element in the x direction. So differentiate this, and we can say that du dx And this is equal to epsilon x. And you see that you differentiate this the first expression, and you get 1 over L negative, and in the other case, you get 1 over L. So this is equal to minus 1 over L, and this is 1 over L. We can make the product, and we can express this as D2